Hello and welcome to this first video in section 13.2. This is on multivariable functions, and to get things started we're going to go ahead and look at something already familiar to you. This is on single variable functions, and so I have this example. F of x is x squared plus 1, and we're going to let x vary from -1 to 2. And here a quick note about notation. This script E symbol, this stands for belongs to. Okay, so I'm saying here that x belongs to this interval from -1 to 2. So put another way, we're just saying that x is a number that's greater than or equal to -1 and less than 2. Okay, so this is a notation we'll see quite a bit this quarter, and I just wanted to point this out right now. Okay, so yeah, back to the function, right? This is just a nice quadratic function, and just take the standard parabola and shift it up 1 unit. Okay, so we're very familiar with things like this, and for the moment, right, just thinking to move towards defining a multivariable function, I want to right now think about this thing in the following way. Okay, so what I have pictured here on the left is just the function's domain, so the interval from -1 to 2. And what this function does is it just takes a number x in this interval, so let's say x is right here, and it's going to send it over here to what we call the range. And the range, right, just consists of all outputs, right? And we refer to these outputs as y, which is just going to be the output for the function f of x, which in this case is just x squared plus 1. And if you give this some thought, right, if you feed this particular function numbers from -1 to 2, for the range you're going to cover the interval from 1 to 5. Okay, so 1 would come from when x is 0, and the 5 would come from when x is 2. And notice, since we're not including 2 itself, this is why we're seeing this circle over here. Okay, so this is a way to conceptualize the function, probably not the most conventional or familiar. So let's go ahead then and put up the graph of what is more familiar. Right, we just see a portion of the standard parabola y equals x squared shifted up 1 unit, right? And the reason why we're just seeing a portion of that parabola is, again, because we have restricted the domain, and so we'll go ahead and put in the domain and range from the left over here in our figure on the right. And looking at, say, this particular input-output pair over here, right, that's just going to correspond to a point on our blue parabola, right? Say this point right here. And we would label this point x comma f of x. Okay, so as we let x vary over this red interval, these corresponding yellow points are just going to trace out this blue parabola. Okay, and on that note, we can go ahead and define the graph of the function, right, just to be the set of all such ordered pairs, x comma f of x, as we let x vary from -1 to 2. Okay, and the thing I really want to emphasize right now is that this graph for a single variable function, so we have just one input x and one output y, right? Its graph is a curve in the xy plane. Okay, now one more quick notational note. XY plane, okay, we're going to denote this also as the following. Script R, this stands for just the number line, the real number line on its own. And since we need both an x and a y axis to build the xy plane, okay, we're going to denote this as r squared. Okay, so we'll use this notation from time to time. Okay, so again, yeah, for single variable functions, one input, one output, their graphs are simply curves in the xy plane. Okay, so with all of that now in our head, let's go ahead and start working towards defining a multivariable function. Okay, so here I've gone ahead and just we're going to start with this example. F of xy is the square root of x squared plus y squared. And notice now, right, I'm not feeding the function a single number. I'm now feeding it an x and a y. So, for example, let's say I feed it a 3 for x and a 4 for y. Okay, so this function is going to take in these two numbers as the input. And then what is it going to do to them? Well, it's going to take the sum of their squares here and then take the square root of the result, right? So here we're going to just get the square root of 25, which is going to give us 5. Okay, so two inputs there and just a single output. Okay, so now what's going on there graphically? Okay, we can conceptualize this much like what we did with a single variable function, but now, right, we need, right, an x and a y for the input, right? So say an ordered pair x, y, and more generally the domain for the function is now going to be not an interval, right, but now it's going to be an entire region in the xy plane, and this function is going to take in one of these ordered pairs and it's going to spit out a number, right? It's going to spit out a number, and this is why you see just a number line here. This is like the 5 we just saw there, and that number will just depend on whatever the function rule happens to be. Okay, and so we'll call this, of course, the range still. Okay, and also note, right, that I've already used x and y for the input variables, so naturally we'll go ahead and just use z for the range variable. Okay. All right, great. So now, much like what we did in the last example, we're now going to put this all together, right, to construct the graph of the function. And so for that, right, we're going to look at some picture like this. All right. And so you can see I now have my x, y, z spatial coordinate system. You see the domain is some subset down here in the xy plane, and we're feeding this function in xy pair. And now for this input-output pair up above, you can think about that in this picture as a point in three-dimensional space, an x, y, z triple, where again z is just determined by the function rule. So for example, in this scenario, right, our xyz triple that would live on the graph of the function would just simply be 3, 4, 5, right? So more generally xy comma f of xy. Now as I let all xy pairs vary over this region here, right, across our domain in the xy plane, right, all of these yellow points are going to trace out what? Well, they're going to trace out now a surface in three-dimensional space. Okay, so let's make a note of that. So our graph now would be the set of all ordered triples, x, y, f of xy, so this is really the z, as we let x and y vary over the domain, again with that, that e notation, that script e. Okay, and again, the big takeaway here is that this graph is a surface in three-dimensional space. Now for three-dimensional space, I'm going to denote this as R3, right? An x-axis, a y-axis, and a z-axis. Okay, so this thing now is going to be a surface in R3. Okay, so what I'd like to now do, here's a few more examples of multivariable functions of two variables. And notice, by the way, when I say a function of two variables, it's really in reference to the inputs, right? So I have an x and a y for the inputs, right? And then there's just a single number for the output. So here z is x squared minus y squared. Sometimes, like we did up above, the function might be written in, say, function notation, right? These can take all kinds of shapes and forms. And so the last thing I do want to mention here in this video, I'm going to go ahead and bring up math3d.org, okay? This is awesome free three-dimensional graphing software. This is like the Desmos of 3D graphing. I put a link on Canvas. I also mentioned this in the syllabus. Okay, this thing is super powerful, really fun to play around with, and visualization is really key in this course, and this thing is going to be a lifesaver. Okay, now for whatever reason, when you open it up, it defaults to this particular surface, and this is the negative y-axis. Okay, so I'm going to go ahead and rotate this around. So we have the positive x, positive y, and then positive z. And also notice here it says explicit surface. So this is really saying z equals x squared minus y squared. So in fact, it's really the same thing as my first example here. It just suppresses the z there. So we have this nice looking Pringle shaped surface, right? Pretty cool looking there. A couple things to note here. So you can mess around with the domain. So for example, I can change the bounds on x. So if I put -5 to 5, I'm just going to see more of the surface. Just like in Desmos, you can change colors. So if I want to say make this thing blue or something, okay, that's kind of nice. Here I'll go ahead and look at, say, another example. So if you want to add something, you always have to click on Add Object. You can't just hit Enter like you do in Desmos. So I'll put in, say, another explicit surface, and let's maybe put in something like that second example, like e to the minus x squared plus y squared, okay? Now you can zoom in and out, which is nice. This is kind of a mound shape. I'll go ahead and put like a 5 in front just to give that thing a vertical stretch. That looks a little more interesting, right? A nice symmetric little mountain shape to the surface. So we're going to be using this a ton. It's going to really come in handy to help us with the visualization side of things. One more thing to point out here, like in Desmos, you can add sliders. So if you click on variable slider, this just brings up the default T for sliders. So for example, if I want to change, say, the amplitude there, just give the vertical stretch, okay, then changing that, oh, really cool, right? And you can do animations. This is really powerful and free, very impressive. So definitely we'll be taking advantage of this. Highly encourage you to play around with it. But that's going to do it for this video. In the next videos, we will get into a lot more examples. For example, why do the surfaces look the way that they do, right? Well, that's more to come. All right, see you next time.